Greetings, my Algebra 2 Padawans. This is Lesson 3.5, Solving Nonlinear Systems of Equations. First, let's remember how to solve a linear system of equations and what we're actually looking for when we're solving a system. So if I look at the system of equations 2x minus 3y equals 3, and the other equation y equals 2x plus 3, they're graphed over here on the side. This actual equation right here, the red line, is that 2x minus 3y equals 3. And this blue line is y is equal to 2x plus 3. Remember what we're looking for when we're solving this system of equations. We're looking for that point of intersection. Where do the two lines cross? What coordinate pair will satisfy both equations in this particular problem? So that coordinate pair is -3, -3. And if we plug -3, -3 into both of my equations, you will see that they both actually work out. So I plug -3, -3 into this first equation. I end up with 3 equals 3. I did the same with the second equation, replacing the x and the y with -3. And I got -3 equals -3. That's the only coordinate pair that will satisfy both equations. So that's what we're going to be looking for as we move forward through this section. So let's move beyond two lines and say, well, we've been talking about parabolas. So what happens if we have a line and a parabola? So here we have a line and a parabola, and let's see of all the things that can happen. So first of all, we could have a line that goes down here and a parabola that is always above the line. And of course, since the line and the parabola do not intersect, this would have no solution to it. Or, if we got it just right, that line and that parabola would in fact touch each other at exactly one point. This, in fact, has only one solution. Or, if we have an equation that goes through there, we have a parabola and it crosses that parabola twice, therefore there are two solutions. Kind of neat. What if we have two parabolas? So here's a parabola, here's a second parabola. Right now, let's say we could have that anywhere. Let's see here. We can have it down here. We could have it over here. We can have it over here. But we can actually draw two parabolas that will not intersect. Or if I did it just right, like just right there, or if I put it down here and just the vertexes touch, or just there, I could end up with a set of parabolas that only have one solution. Or if I did it just right, I can have a parabola that has two points of intersection. So when we're looking at systems of equations that are nonlinear, so we have a parabola and a line, or two parabolas, we can have no solution, one solution, or two solutions, depending on how they line up graphically. So let's take a look how to solve a system of nonlinear equations by graphing. So the good news is when we graph a parabola, it's going to be exactly the same way as we had done them before. So we can either create that table of values, we can find the vertex, and then create the table of values. We can graph that however we like to. So this this x squared minus 2x minus 1, we can graph that quadratic equation however we want to graph that, whatever works best for you. And then the linear equation, y equals -2x minus 1, well, that should be really easy for us to just plot the y-intercept and then use the slope to come up with the rest of that graph. So why don't you pause the video right now and make sure you remember how to graph a quadratic equation and a linear equation. So to graph the quadratic equation, I know the vertex is at 1, -2, and of course I got that by using the opposite of b over 2a. Since my quadratic equation is in standard form, I did the opposite of b over 2a and got 1. Plugged that 1 back into my equation, I came up with my -2. So I can plot the point 1, -2. Because the a value is equal to 1, I know that I can follow that pattern of 1, 3, and then 5, if that would fit on the graph, which it doesn't. And then use my axis of symmetry to come up with those other coordinate pairs, and I can graph a fairly accurate quadratic equation. As far as the second equation, y equals -2x minus 1, again, I use the y-intercept, and I go down 2 over 1, and down 2 over 1, and I can get a couple more points on the other side, and I can, in fact, draw that linear equation right there. So what we're looking for is we're looking for the point of intersection. Where does the parabola and the line cross? And it's right there. I used Desmos to graph this, So this graph is much neater because Desmos and technology did it for me, but you can very clearly see the point of intersection is in fact at 0, -1. And real quickly, if we wanted to check that solution, we could take the point 0, -1 and plug it back into both of my equations, which is what I'm going to do right now. And you'll see that when I do that, both equations actually both equations are satisfied by the coordinate pair 0, -1. But what if we don't have Desmos? How do we solve them algebraically? Well, it's actually not going to be much different than what we were doing before when we were solving linear systems of equation, except we're going to focus on using substitution. And I would encourage you to use substitution. Elimination can get really weird with quadratic equations. So I'm going to really focus on solving using the substitution method. The first thing before you start using substitution is you have to make sure they are always in the form y equals. So we're going to take both of these quadratic equations and we're going to put them in the form y equals. So for the first equation, I'll add y to both sides and I'll add 1 to both sides. And I'll end up with y equals x squared plus x plus 1. For the second equation, I'm going to end up subtracting x from both sides and keeping the 4 right exactly where it is. And I end up with the equation of -x plus 4. So now once I have both equations solved for y, I'm going to take both of these equations and set them equal to each other. See how they're both set equal to y? See how it's y equals and y equals? So what we're going to do is essentially we're going to take the y and make the y equal to the y. What I mean is take the two equations and set them equal to each other like this. And now it's just like what we were doing in the previous section. We're going to solve this quadratic equation. How do we solve it? Well, I'm going to always set it equal to 0 first. So I'll add x to both sides, I'll subtract 4 from both sides, and I'll end up with the equation x squared plus 2x minus 3 equals 0. Now, at this point, it's up to you. What method of factoring quadratic equations do you like the best? Do you like the quadratic formula? Do you like factoring? Do you see how to factor this? Now, I in fact do see how to factor this. I know that x squared plus 2x minus 3 factors down to be x plus 3 times x minus 1. So I'm going to solve this by factoring. And I'll come up with two x values of -3 and +1. So these are the actual two x values of the point of intersection of this quadratic equation and this linear equation. But those are only the x values. So once I have the x values, I need to take the x values and plug them back into the original equation. So I'm going to take y equals -3, and I'm going to plug that into, I think, my second equation. That seems like that may be the easiest one to solve for. Oops, that's x equals -3. So y is equal to negative, and then x is equal to -3 plus 4. If you like, you can put that 1 in front of that if that helps you to see that double negative a little bit better. And I end up with 7. So one of the coordinate pairs for the solution is -3, 7. Let's find the other one. So I'll take that x equals 1, and again, I'm plugging that into the second equation, -x plus 4, which will again give me that would be 1 plus 4, which is equal to 3. So my second coordinate pair is 1, 3. So that's my solution to this system of equations. Let me just show you what that looks like on Desmos so that you can see what these two equations are equal to. So I took those two equations and I plugged them into Desmos, and you can verify our two answers of -3, 7 and 1, 3. That's the 2 points of intersection, right here and right here. Let's take a look at another system. So the first thing I'm going to do, as I did in the last problem, is I'm going to take each one of these equations and I'm going to set them equal to y. So I'll get them in the form y equals. Now I'm going to take these two quadratic equations and set them equal to each other. Once I have the two quadratic equations equal to each other, I'm going to set them equal to 0. So I'll do that by adding x squared to both sides and then adding 2x to both sides. So that will get me 3x squared minus 3x plus 2 equals 0. Now, I don't know about you, but I can't think of how to factor 3x squared minus 3x plus 2. I can't think about how to factor it. That doesn't mean we stop and we don't solve this problem anymore. What it means is we have to use a different method. And of course, if I get something that's not factorable, I'm going to use the quadratic formula. So x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And I simplify that down. Let's see here. I get x equals 3 plus or minus the square root, negative 3 squared is 9, minus 4 times 3 times 2 minus 24 over 6, which is 3 plus or minus the square root of negative 15 over 6. I'll simplify my radical, but really there's nothing else that I can really do here, so I get 3 plus or minus I square roots of 15 over 6. I got an imaginary solution for my system of equations. Well, if you remember back in what we were talking about when we were looking at graphing, if we got imaginary numbers when we were looking for x-intercepts, it didn't have any x-intercepts. So if we get imaginary solutions when we're solving a system of equations, guess what that means? These two quadratic equations do not intersect. As a matter of fact, when I plug them into Desmos, this is what I get. And you'll see that the blue line and the black line do not cross anywhere. So this solution to this system of equations is in fact no solution because the quadratics, the parabolas, do not intersect. So we're at the point where I would like you to try to solve a couple of these systems. So if you would please pause the video right now and try these 3 example problems. And then of course we will work out the solutions together when we resume the video. But right now, pause the video and try out these 3 problems. So the first step is, of course, to set these equal to y, and this system of equations is already in that form, so there's no need to do any work for that. So the first step will actually be then to take these 2 quadratic equations and set them equal to each other. And then we will solve and set this equal to 0. So I'm going to add x squared to both sides, and I'm adding x squared to both sides so that it's not negative anymore. And I'll subtract 4. That will get me 0 equals x squared minus 4x plus 4. Be really careful. Don't combine these. They're not like terms. From here, I'm going to solve this quadratic equation. So I'll think about the pair of numbers that multiplies together to give me 4 and adds together to give me negative 4. And I end up with x minus 2 times x minus 2. So my value will then be, when I set that factor equal to 0, I get x is equal to 2. I'll then take that 2 and I'll plug that into one of my equations. How about the second one? Oops. And I get y is equal to negative 4 times 2 plus 8, which will get me, let's see here, that's negative 8 plus 8, which is 0. So my point of intersection is 2, 0. So I only came up with one solution, right? Because that would get me the same value again. So there is only one point of intersection here. If you would look at these 2 things in Desmos, you would see that they only intersect at one point. Number 2, same idea. We're going to set these equations equal to y, make them in the form y equals. Then we will take these 2 equations and set them equal to each other. Now, of course, we will manipulate this equation and get it set equal to 0. That'll get me 0 is equal to x squared plus x plus 5. Now, I can't think of a way to factor this because I can't think of a pair of numbers that multiplies together to give me 5 and adds together to give me 0. So I'm going to use the quadratic formula to solve this quadratic equation. And I get to this point where I have negative 1 plus or minus the square root of negative 19 over 2. Now, once I see here, I realize that I'm going to have an imaginary solution because I have a negative underneath of the radical. So the second I know that I'm going to have an imaginary solution, I'm probably going to stop and say, hey, this system has no solution. These 2 equations will not cross. This parabola and this line do not intersect anywhere. And again, take time right now to verify in Desmos what you actually see when you type in these 2 equations. You will see that they do not, in fact, intersect. And finally, our last one, number 3, 2x squared plus 4x minus y equals negative 2, and x squared plus y is equal to 2. These 2 parabolas, these 2 quadratic equations. Again, we're going to set them equal to y, make them in the form y equals, and then set them equal to each other. It looks like this. And now once we have this, of course, we'll set this quadratic equation equal to 0. And this is really nice because I have 3x squared plus 4x equals 0, which this is factorable. We have a GCF factoring. Don't forget about that. Sometimes the easiest way to factor is, in fact, to pull out a GCF. And that's actually what I can do in this problem. And then I can set each one of my factors individually equal to 0. I'll get x equals 0 for one of my solutions. And the other, after I solve it here, I'll get x equals negative 4/3. That's the second x value of the point of intersection. Now, once I get these, of course, I can take x equals 0, and I can plug that into one of the equations. I don't know, I kind of like the second one. So x squared plus y equals 2. So I'll plug in 0. That's 0 squared plus y equals 2, or y is equal to 2. So one of the coordinate pairs is 0, 2 for a point of intersection. And the second one, I'll take that x equals negative 4/3, and again, I'm going to plug that into x squared plus y equals 2. Now, I'm going to have to do a little bit more math here, right? This one's a little trickier, but it's a good thing I have my calculator, because my calculator will allow me to solve this a lot easier. And I'll end up with 2/9 is my final answer. And again, that's just me taking 2 and subtracting 16/9 from that and keeping it in a fractional form. So my solution will be negative 4/3, 2/9. It's a 3. And again, you can verify that in Desmos, although I will tell you, Desmos is probably going to give you the decimal answer when you click on that. So you would see the decimal answer of negative 1.333, 0.222. So just so you know, that's going to be an approximation. That's not the exact value. That's only the approximation. This is the exact value. All right, folks, that's all I got for you now. Good luck on your assignment, your classwork when you work on that tomorrow. See you later.